So today we are going through advanced aircraft systems. We're going to be covering a few systems that are a little bit more basic in nature. They're from the knowledge test. And then we're going to cover just a few items on advanced systems that, because you're going to be a commercial pilot flying a bigger airplane someday. You need to know a little bit more about some systems here. So a few basics before we get started into the advanced stuff. These are going to be a little bit more pertinent for the knowledge exam, as the FAA may ask you questions on these. We do have a little discussion slide if you want to enter some questions in there. The first one to talk about is carburetor ice. For the most part, we are not flying any carbureted aircraft other than the seaplane, but we've gotten rid of most of our carbureted airplanes. I think we have one more Seminole remaining that's still carbureted. I'd have to check on that. But for the most part, you are flying fuel injected aircraft. So there's a great benefit to that, is you don't have to worry about carburetor icing forming. So when we think about carburetor icing, we have to think of a couple parameters. First of all, Bernoulli showed us that there was a pressure drop through a venturi, and that's what we have going through in this area right here as a venturi. So the airflow is coming through that restriction. Pressure drop also gives you a temperature drop. So that's half of what's causing the temperature to go down. The other part is this vaporization of fuel. Anytime we vaporize fuel, we also cool down the surrounding air. We're actually taking energy from the ambient air and using that to vaporize the fuel. We're adding it into the actual fuel. That causes a temperature drop as well. So the two of those could result in what we see over here in the picture of carburetor ice forming. So you're looking at a butterfly valve in the throat or in the venturi of a carburetor. And so it's just completely iced up in there. In this case, this is enough ice to actually kill the engine, to prevent the airflow, the fuel mixture from getting into the engine. So it can be problematic. We can have this, especially when temperatures are below freezing or even well above freezing. You know, the book tells us 70 degrees, but it could be 80 degrees out. It could be 90 degrees out. So you can still get carburetor icing. It just depends on how much moisture content is in the air. And the more moisture you have, then the greater the chance of getting a carb ice situation. And that can be carb ice from anything from idle power to cruise power to full power as well. We get rid of it with carburetor heat, and carburetor heat is going to add hot air in. So when we think about that volume of air, and if we were to actually weigh the number of air molecules in it, there would be fewer air molecules in that volume of air. So fewer air molecules means you have a richer mixture setting. So when you turn on the carb heat, it is a richer fuel setting, and that's going to be an FAA test question, right? What happens to the mixture when you use carb heat? All right, so turning on carb heat, hot air enriches the fuel mixture. You lose power. Okay? You absolutely lose power with that. Okay? There's not as many air molecules. Remember how we talked about the other class period? The more air molecules you have together, the more engine performance you get. This is a reduction of those air molecules, so a reduction of power. Now, bless you. Now, the book does not give you the full story on carb ice. When a pilot activates carb heat, the book says you get a drop in your manifold pressure, which is true. Right? But what happens to all of that ice that as it melts? It turns into water. Where does the water go? The water goes through the engine. It goes right into the cylinder. Water does not ignite. Water cools things down. So when that water gets into your cylinders, it is going to further reduce your power. And water does not make the engine burn very well, so it's going to run very rough while the water is melting. Your books do not tell you that. Once all the ice is out of there, it means all the water has moved through the engine now, been vaporized in the cylinder. You'll notice an increase and smoother running engine. And then that's your clue that you can turn off carb heat at that point. So just keep a couple things in mind, right? If you're dealing with a fixed pitched propeller, RPMs will degrade with carb ice and carb heat. But what if you're running a constant speed propeller? Ooh, that's different. As soon as you can start getting carb ice, you lose power. And the blade angles go shallower to keep the RPM the same. As more ice builds up, blade angles keep changing shallower to keep the RPMs up. So tachometer doesn't help you on a constant speed engine. It's going to be manifold pressure, reduction in manifold pressure. You always got to think about what type of propeller system am I using here. All right, so top hat question for you. Carburetor ice can form with temperatures as high as 70 degrees, but could be warmer. Which of these statements would be true with that? All right, nice job. Enough moisture in the atmosphere. You all got it right. Another question for you. Applying carburetor heat will make the fuel-air mixture. Remember hot air? What does hot air do to the number of molecules? The number of molecules really is dependent upon the amount of power that can be developed. Well, most of you got that one right. Fewer air molecules means more fuel is in the mixture. So that would be a richer setting. All right, next bit is going to be on ignition. You're going to be asked a question on your knowledge exam about a broken P lead. So we need to understand what is a P lead, how is it working in our ignition system. Of course, you know that the ignition system is not dependent upon a battery in an airplane. Therefore, we have something to generate that electrical impulse that goes to the spark plug, and that's going to be from the magnetos. And we remember there's two magnetos, one for redundancy, two for more even flame propagation inside the cylinder, and that each of the magnetos is connected to half of the plugs in the engine. In order to make this work, we need an electrical circuit. So remember, basic electricity requires a positive lead and a negative lead. Each of your spark plugs, which are down here, labeled 1 through 4, they are grounded right to the crankcase. So there's one half of the electrical connection for you. The other half of that connection comes from the positive lead, or the P lead, as labeled here. So we'll take a peek here. The arrow and the gray circle is your key switch. And currently the arrow is pointing to the letter B, which is indicating both magnetos. You want both magnetos running. So you have engaged the positive lead from each of the magnetos here. Now let me run the animation for it. When the engine is turning, the magnetos are turning, they hit the impulse point and send the electrical impulse to each of the plugs. I've slowed this down quite a bit, but this is what's happening many times per second inside your engine. That's because we have the positive lead completing the circuit through the plug's grounding. So that's all normal operation right there. Now let's understand what happens when we switch the key to a different magneto setting. Remember, at the beginning of your flight, while you're on the ground, you're doing the power check and you're switching to each individual magneto. So this is what's happening in there. We rotate the key, for example, to the L position. Okay. That means we want the left magneto to run. We want to ground out the right magneto. So we change the P lead connection and we break the circuit. The right magneto is no longer completing the circuit through the spark plugs. It is being grounded out. In other words, that means it just doesn't produce any electrical impulse. So as the magnetos turn, only the left magneto is firing. The right magneto hits the spark point, but it's grounded out and does not work. And of course, you're checking to make sure that the mag drop is within a certain number of RPMs. And just to show you the right magneto here, we move the key switch to the R position. We are saying that we only want the right magneto to work. We're going to ground out the left magneto. So the left magneto is no longer grounded through the spark plug, but the right magneto still is, and we can check that magneto. So that's all normal that you do before the flight. After your flight, you're back on the ramp. Part of the shutdown checklist is for you to go through and turn the mags to the off position momentarily. And this is where you're checking for the broken P lead. So as we move our key switch to the off position, we are actually grounding out both of the magneto P leads. We're breaking the circuit on both magnetos, and therefore they're no longer grounded at the spark plug. Now the engine's got momentum, so it's going to keep spinning, but there's no spark occurring. And we hear a drop very quickly on the RPM, right? If we don't have that drop, that means one of the P leads is broken, right? And is still currently making the circuit. So that's the key here, is understanding a broken P lead means I can't ground it here at the key switch. And that means you still have a circuit with the spark plug. You may have heard some people call this a hot magneto. So you could literally go up and hand prop the engine with a hot magneto. And if there's fuel in the line, that magneto will spark, send it to the plug, and any fuel inside that cylinder will ignite, and you could get the propeller blade to turn. And if it has enough fuel, it could continue firing and start operation again. So that's why we're checking to make sure we don't have a broken P lead there. So let's try a top hat question here. Broken P lead, what does it mean? All right, most of you did get that one right. So a broken P-lead, you see from the left magneto, means that circuit is still grounded through the plug. Circuit's still made. And it will fire if it hits its lead point. All right, another basic system is the oil system. Lifeblood of the engine. Oil does provide a lot of different functions inside the engine. Lubrication is one of the most important one. It also provides a small film so you don't have metal to metal contact between parts. Especially in the cylinders, but throughout the engine, it provides cleaning. It also provides heat dissipation. We can remove heat from these moving parts. And it also provides a corrosion resistance. You don't want something to corrode, put oil on it. The way we've got a thin layer of oil prevents the air contact with it and moisture. So oil is extremely important for your engine. If you don't have it, your engine will not run very long. It'll get too hot, then you'll find metal seizing up inside and you'll just have a hard stop of the engine without oil. And it does not take very long for that to happen. Two types of systems. Let's go through the parts here first. We have some type of sump system that oil is gathered into. It's then pulled through a screen and it will go through the pump and then go through a filter and then go through the various flows and channels inside the engine itself. Now that sump position, whether it's with the engine or outside of the engine, will determine what type of system we have. You are very familiar with the wet sump system because our oil is contained internally with the engine. And you measure that by pulling out the dipstick right there at the engine every time. There are some aircraft, especially older ones, that have a dry sump system where oil is contained not in the engine, but somewhere else in the fuselage or wing, and they pump it to the engine. So that's a dry sump system. Hopefully you were able to watch that quick 20-minute video on the 1937 Chevrolet V8 engine and how lubrication works in it. The neat thing about that is pretty much how our airplanes are lubricated today. Right? So that technology they developed back in 1937, it's still happening. Of course, we depend upon a gear pump, and notice how oil flows to the outside through the gears, never in between. And that provides the pressure that allows oil to be moved through the engine system. Inside the engine itself, we have oil being splashed on parts, being sprayed onto parts, or flowing through different channels to help cool and lubricate different parts. So it's just important to understand that these engineers have gone to great lengths to make sure every part of your engine is getting the flow of oil. Because oil is so important to the engine, you have to make sure that at startup, you have oil flowing. So one of the first things you should be looking for after you are done cranking is that you have oil pressure. And so we're looking for oil pressure if it's the warm months of the year, within 30 seconds of the engine start. And if it's colder months, it's more viscous of a flow, then you have 60 seconds in which you get oil pressure. Otherwise, outside of these parameters, your oil's not flowing properly and you're damaging your engine, then you would need to shut down. All right, that's the end of the basic section here. No questions on written there. Any verbal questions? All right, we're all happy. Yay.